I will cover this topic, AFM diagrams and the conclusion. In the ACF and AKF diagram, FeO and MgO plus MnO are grouped as one component. This simplified make it possible to represent many observed minerals assemblages, but certainly not all of them. For example, in some rocks, biotite is present together with muscovite and one of the polymorphs of Al2, SiO5, kyanite, andalusite and sillimanite, whereas in other rocks, biotite coexists with garnet, sterlite, quartz, muscovite. These assemblies cannot be shown in the AKF diagram due to the simplification of treating MgO and FeO as one component. Although Mg and Fe plus 2 substitute each other in this lattice of silicates, the extent of this isomorphous substitution is different for the various coexisting minerals and further more depends on the bulk composition of the rocks, temperature and pressure. Thus, in contrast to the ACF and AKF diagram, FeO and MgO are treated as two components. In this case of AFM projection, this projection is particularly assemblages of peltic rocks, except at the highest grade of metamorphism. These rocks contains muscovite to cover the variation in muscovite bearing cyst. Thomson in 1957 developed a projection based upon a tetrahedral plots of the four components A equal to Al2O3, K equal to K2O, F equal to FeO, MnO and M equal to MgO. Any muscovite bearing assemblies can be represented graphically by projected each pertinent points in the AKFM tetrahedron onto the AFM diagram plane by a straight line drawn through the muscovite point P. Every such assemblies contain muscovite and may contain quartz and or plagioclase in addition to the phases connected by the line in the AFM projection phases whose composition lie on the tetrahedral sector. PAFM projection within the AFM triangle itself. Examples are almandine, sterlite, chlorite, chloritoid, etc. Others such as biotite located in pyramidal sector PO and FM plots below FM join. Note that the point of potash feldspar when projected along a straight line originating in point P intersect the AFM plane only at indefinite. This is indicated by arrow near the mineral potash feldspar. The geometrical projection of the point inside the tetrahedron on the AFM plane is carried out in actual practice by the mean of calculation. First of all, the weight percent of the oxides are converted to molecular proportion A and M, which serve as coordinates, and these are calculated as follows: A equal to under bracket Al2O3 plus Fe2O3 minus under bracket 3K2O plus Na2O plus CO whole divided by under bracket Al2O3 plus Fe2O3 bracket close minus 3 under bracket K2O plus Na2O plus CO plus MgO plus under bracket FeO plus MnO and whole together under bracket. M equal to MgO divided by MgO plus FeO plus MnO. A value is thus excess Al2O3 after subtracting the amount consumed in albite, anorthite, plagioclase and muscovite. The chemical formula of muscovite is K2O, 3Al2O3, 6SiO2, 2H2O, and therefore 3K2O is subtracted from Al2O3. If the A value where a biotite is calculated, it becomes appear that this must be a negative number. For example, K2O under bracket MgFe5 Al under bracket Si5 Al3 bracket close O2 O under bracket OH twice, therefore, A equal to minus 0.2, and for K2O MgFe6 Si6 Al2 O2 O OH4, then A equal to minus 0.5. The AFM projection, which has been described above, apply only to the mineral assemblages containing muscovite and quartz as additional phases. However, other AFM projection has been constructed for the rock devoid of muscovite and containing potash feldspar. Barker in 1971. This is commonly called A-F-M' diagram projection, in which case point of minerals and rocks that are situated within the K2O Al2O3 FeO MgO tetrahedron are projected on the Al2O3 FeO MgO planes by using potash feldspar as the points of projection. The scheme of calculation is A dash equal to Al2O3 plus K2O minus under bracket K2O plus Na2O plus CO, F equal to FeO plus MnO, and M dash equal to MgO. Therefore, the A dash plus M dash plus F dash equal to 100 in molecular percentage projection from apical examples. The ternary system CO, MgO, SiO2 is straightforward. C equal to CO, M equal to MgO, and S equal to SiO2. Plot the following minerals. FO, which denotes phosphorite, the chemical formula is Mg2SiO4, periclase MgO, anisotite MgSiO3, quartz SiO2, diopside CaMgSi2O6, calcite CaCO3. If you will plot these member on CaO, MgO and SiO2 diagrams, see the diagram on screen and position of these minerals. In this modules, I have discussed about the graphical representation of minerals assemblages. I have covered the whole topic under the following heads: the phase rule, simplifying degree of freedom, simplifying components, metamorphic phase diagrams, ACF diagrams, method of calculation, AKF diagram, AFM projection. The most commonly used chemographic diagrams are the ACF, AKF, AFM, A-, F-, M-, and CO, MgO, SiO2 diagrams. These chemographic diagrams are graphical description of phases, composition and coexisting phases relationship. Most are triangular diagram that show a particular metamorphic grade or a limit pressure temperature range. When a diagram reveals an anomaly such as crossing the tie line, the reason can generally be found by turning to a mode system C more than 3 and the original Gibbs phase rule.